Welcome learners. In today's lecture, we are going to start the sixth chapter, which is all about capacitance from the course book of Engineering Electromagnetics, 9th edition by William Haith and John Buck. And again, capacitance is something that we have studied or you might have studied in your previous courses, which talks about the measure or capability of a device to store energy. So capacitance basically is something related to the measurement of a device, or it's a measure of any electrical device, to store energy. And we have previously seen how we can represent the equation of energy. The contents of this chapter will be, we'll look into the capacitance, its numerical valuation or the equation that can be utilized to solve different problems. Then we look at the example of a parallel plate capacitor, and then we are going to just have a look at two of the important equations widely utilized in the field of electromagnetics, and that is Poisson's and Laplace equation. And these equations basically help us to figure out the relationship between potential difference and the charge density. So we begin with the first topic, that is on capacitance, and as we mentioned that it measures the capability of energy storage in any electrical device. For example, you might have seen the capacitance being utilized as a sensing device in your cellular phones, like sensing or capacitive touch on your screens, and sometimes the capacitance appears as a byproduct, for example the parasitic capacitance, which you may see on PCB devices or the mutual coupling between the metal traces. So capacitance is also defined as part of a device which is known as a capacitor, and its basic purpose is again to store electric fields or store energy, as we say. So if we talk about the storage of charges and the storage of electric fields, so we have previously seen that the energy stored in the form of charges is represented as the summation of charges and the product of their potential, where the value of m is 1 to n. Similarly, if we are talking about the storage of energy, as we saw in the previous discussions, in terms of the fields, it can be represented as the relationship between the electric flux density and the electric field intensity over a volumetric distribution. So these are the two expressions of the energy stored in form of charges or in the form of field lines. Similarly, we can also look that the energy stored in a capacitance from our previous examples or previous understanding of the topic is half CV square. So if we talk about the energy stored of a parallel plate capacitor in general, it is basically half CV square. So this is something that we already know, or you should already know, and these two equations on your left and right are something that we have seen in our previous discussions. So now let us come to capacitance and see how well we can understand it with a simple analogy. So consider in the first figure we have two parallel or infinite plates. In this case, let's say they are finite plates. One plate is positively charged, so we can say that the surface charge distribution is plus rho s, and one plate is negatively charged, so that can have a value of negative rho s. And since these two plates have a dielectric material or medium between them, we know that the electric field will be formed and it will flow from the positive side to the negative side, as seen in the B image. So this is the movement of the electric potential between the two plates inside a dielectric medium. So we can say that the total net charge of this system is 0, and all the charges are confined inside this region of the capacitor plates. So once these conditions are created, we can see that an electric field is already formed here. So if the electric field exists, then the potential difference can also be figured out between these two plates. So we say that capacitance in this scenario is defined as the ratio of the total amount of charges on the two plates to the potential difference existing between them. So this is how we define a capacitance, and its unit is normally in farads. So capacitance is the ratio of the magnitude of the charges at either plates to the magnitude of the potential difference between the plates. And another way to write this capacitance is if we go back to our analysis in the third chapter, that the Gauss's law basically tells us what the total charge can be in an asymmetric or a symmetric confined surface. It is the product of the surface enclosed electric flux density in a smaller surface. And similarly, we already know how the potential can be figured out, that is negative d dot dl upon epsilon, or another way of representing the potential is E dot d of L. So once we know the values of the charge and the potential, then the capacitance, which was the ratio of the total charge to the potential difference, can also be represented as such. We have taken the value of the charge in terms of the Gauss's law to the ratio of the potential in terms of the electric flux density. So in this is another way of utilizing the values to find the unknown capacitance. So we now have two equations that can be used or can be helpful in finding the capacitance and the associated values of charges and potential difference. Now let us come to the practical example of capacitance in terms of a parallel plate capacitance, and what can be the value if we have an infinite plates. One is positively charged, having surface charge distribution of positive s, and another is negatively charged, having the value of negative rho s, and the medium between them is a dielectric medium. So again, the electric field will flow from the positive charge towards the negative charge, and the potential difference can exist. We can represent again the value of the charges as per Gauss's law to be the value of electric flux covered or even with the area of A, or separated by area A, and the potential is basically the electric flux density, the separation d per unit the material's permittivity. So thus, utilizing the capacitance equation, we can find for the parallel plate capacitor, the equation comes out to be dependent on the material's property, the separation between them d, and the area between the plates, which is A. In some of the books, you may also find this expression written as epsilon s by d. So again, they both are the same. S and A are basically representing the area inside the parallel plate capacitor. And one thing again, just a reminder that the energy associated with the parallel plate capacitor is half CV square, where V is the potential difference and C is the capacitance of the system. So this is the equations utilized for a parallel plate capacitor, and it will be helpful for us in solving different problems. Now let us look at a problem where we can utilize the previous equations in finding for example, in this case, we need to find the relative permittivity, which means we need to find the epsilon r of a dielectric material present inside a parallel plate capacitor if in the first part the area is 0.12 meter squares, the distance or separation between the plates is d 80 micrometer, potential difference is 12 volts, and the capacitor contains an energy W of 1 microjoules. So let us solve the first part, and then we can go to the remaining parts. Okay, so in the first part we need to figure out what is the permittivity inside this parallel plate capacitor, or the materials property. We have been given the value of the area, the distance, and the potential difference. So we can go different ways for this. Let's start with the simpler one. We know that the energy stored is half C V naught square, and we also know that this energy can be simplified or written as, so the capacitance basically for a parallel plate capacitor is represented as ES divided by D, or it can be EA divided by D. Both represents the same thing, V naught square. Then we can say it is half. Epsilon can be broken down into absolute and relative permittivities divided by the distance and potential difference square. So now we can basically solve this portion to get the value or the answer. So the energy is already given to us, so WE is 1 microjoule, so I can write it 1 into 10 raised to power minus 6. It is equal to half. The value of E naught is already known, so it is 8.85 into 10 raised to power minus 12, and ER is something that we need to find, multiplied by what is the potential difference, it is 12. So I can write it as 12 square, but first let me use the value of d, that is 80 into 10 raised to power minus 6. So let me separate it as such, and then potential difference comes out to be 12 volts or 12 square. So this is 12 square and this is it. So once we input all the values and do the multiplication, then value of permittivity comes out to be 1.045. So this is the solution, and we can see that this is almost equal to that. So this is the answer which we are getting for the permittivity in the first part. Now let us come to the second part. The second part is again asking us to find the relative permittivity, but this time the stored energy is 100 joules per meter cube with a potential of 200 volts, and the separation is 45 micrometer. So we have been given that the energy stored is 100 joules per meter cube, and we can utilize the distance and capacity as such that the total energy density is, so the total energy density, which means the energy per unit specific area, is dependent upon the energy that you have covering the distance and the potential in meter square. So this is basically your area, 0.12. Okay, I think I forgot the value of this s, so this s has to be here because this is 0.12. So let me write the value of s over here. So it is 0.12 as well. Okay, don't forget this is 0.12 that we have to multiply, so that we'll get the correct answer over. Okay, so this is 0.12 meter square. So the total energy density, so this is the equation of energy density which involves the energy in a separation of the elements and the area that is covering. So it comes out to be 5.4 into 10 raised to power minus 4 joules. So this is the complete energy density that we have. Now once we have this equation, we can move forward by using the equation of the capacitor energy, which is half CV square, which means the energy density is 5.4 into, or let me rewrite the equation because we need to find the permittivity. So I can write this equation in the form of C. So C is equal to 2 of WE divided by V square. Now we use this equation to get what we need. So it is going to be C equals to 2 into 5.4 into 10 raised to power minus 4, and then you divide it by potential difference is 200 whole square, and this comes out to be 27 into 10 raised to power minus 9 farad. So this is the capacitance value. Once we have the capacitance value, then you can use the parallel plate capacitors equation to get the permittivity, and that basically is that ER. So I'm just writing the equation now. Permittivity is equal to the capacitance, the separation D divided by the area and the permittivity. So basically I have utilized this equation over here. Okay, where absolutely okay. So once these values are known and we know what is C from this value, D is already given to us as 45 micrometer, S is 0.12, and epsilon is the relative permittivity in free space. So I'll just write everything for simplicity. 27 into 10 raised to power minus 9 multiplied by 45 into 10 raised to power minus 6 divided by 0.12, and then we have 8.85 into 10 raised to power minus 12. So the final permittivity for the second part comes out to be 1.14, and that's the solution. Coming to the final part, again a very simple solution to the final part. We have been given the electric field intensity and the surface charge. So the value of E is given, which is 200 kilovolts per meter, and the surface charge distribution is 20 microcube per meter cube. We need to find permittivity, so this is straightforward. We know that the electric field intensity of a sheet charge distribution is rho s divided by 2 epsilon, and so this is for one sheet. When we have two sheets like a parallel plate capacitor, this will be epsilon only. So this is rho s divided by epsilon. Then we can say the epsilon can be divided into epsilon naught into epsilon r, and thus the epsilon r can be figured out from here. That is going to be the rho of s divided by electric field multiplied by epsilon naught. So now we have the value of sheet, that is 20 into 10 raised to power minus 6 divided by electric field is 200 K, and multiplied by epsilon, which is the permittivity of free space. So permittivity or relative permittivity comes out to be 11.29. That is E of R, and this is the solution to the final part of the problem. Okay, so now let us see what we have learned so far. So far we have learned the relationship between electric flux density and electric field intensity, and we know that the point form of Gauss's law is basically the divergence of electric field or electric flux depending upon the volume charge, and this is also known as the first Maxwell equation. And we know the relationship between finding the potential and given electric field, that is the gradient of the potential. So now once we have all this data, can we have another set of equation that can help us to figure out the volume charge distribution? If we know the potential difference and the electric field, is there an easy way to find this potential or the volume charge distribution from the potential and electric field? And yes, there is. So we can directly find this rho v by using two famous equations, or basically a single famous equation that is known as Poisson's equation, and from there we can generate a second known equation, that is the Laplace equation. So the Poisson equation that can help us find the value of the volume charge density is basically you take the square or double derivative square of the potential, which is equal to the negative of volume charge distribution per unit the epsilon or the permittivity. So this equation is known as the Poisson's equation, which can help us locate the volume charge distribution on any given material. So how do we accomplish this? So we know that the point form of Gauss's law is such, or also known as the Maxwell's equation. If we replace the value of d with epsilon E, so here you can see d has been replaced with epsilon E, and then the electric field is replaced with the negative of gradient of V. Thus we equate everything equal to rho V, and then if we take the divergence of this gradient value, we get the Poisson's equations of negative rho V by V, where this operation is basically a square of the potential and it equals to this value. So this is basically the Poisson's equation. And why this is important? Because it provides the relationship between the electric potential. So Poisson's equation is important because it shows the relationship between the potential and the volume charge distribution. So we can easily find both of them if we have been given this relationship. And now once we have this kind of a relationship and we want to further analyze it, we can move from Poisson to what is known as a Laplacian equation. And Laplacian is a special case of Poisson where we make the volume charge equal to 0 in the Poisson's equation. Thus we get a Laplacian operator or Laplacian equation, which is basically del square V equals to 0, and this is particularly useful when we want to model potential differences in empty space between conductors. So this del operator is the del square or the Laplacian operator, and this equation is basically for the Laplacian. So the Poisson's equation is this one, again del square V, and if you make rho V equals to 0, you get the Laplacian operator. Important parameters to find the del square V in the Cartesian coordinate system, cylindrical and spherical coordinate systems are shown, which we are going to look into our analysis with an example. So now let us look at an example and figure out how to find the del square V operators by the coordinate systems given. So in this problem we have been asked to find the value of potential and volume charge distribution rho V at point P in free space. So in the first part the potential is given at point P, then in the second part again potential is given at this point of P, and in the third part potential is given at this P. So let us start with the first part and see how we can find the potential and the volume charge distribution. So the data is that V is equal to, or potential is given as 4yz divided by x square plus 1, and we need to find potential at P. So that is straightforward. You just input the value of P, which is 1, 2, 3 in equation. So you will get potential at P, which comes out to be 4 into 2 into 3 divided by 1 square plus 1, and it comes out to be 12 volts. So this is the solution to the first part of part A. Okay, now once we have this, we need to find the second unknown, which is the volume charge distribution. So we know that Laplacian operator, or basically the Poisson's equation, del square V is equal to minus rho V divided by epsilon. So this is the equation that we can use to find rho V. So in order to utilize this, we need to know what is del square V. So first let us operate on del square V. So del square V is basically the double derivative or partial derivative of del square V divided by del x square plus del square V divided by del y square plus del square V divided by del z square. Now let us do these one by one. So we start with the first part, then we solve the second partial derivative, and then we solve the third. So we start with the first partial derivative. We basically want to solve del square V divided by del square, which is del square by del square, and what is the value of V? It is 4yz divided by x square plus 1. Okay, so if you want to solve this, so what is the first partial derivative of this value? So it is going to be, since it's with respect to x, so I can bring out the coefficient 4yz, and I have to do the double derivative of 1 divided by x square plus 1. This is what I want to do now. So I can use this space and say that I have 4yz, and I want to figure out the first partial derivative with respect to x of 1 divided by x square plus 1. So once you do the partial derivative, how can you do the partial derivative of such kind of a value? So you might remember this representation, that whenever you have this kind of a fractional value, you can use different methods, but one of the method is that you take the denominator, you multiply it with the derivative of the numerator, then you subtract it from the numerator and you multiply it with the derivative of the denominator, and then you divide it by the square of the denominator. So this is an expression that you can use. So let us apply it over here. So this equals to 4yz partial first derivative, and once you take this equation, so you take the denominator, which is x square plus 1, then you take the derivative of the numerator, so one derivative is 0, then you again take the numerator, then you take the derivative of the denominator, so x square plus 1 will be 2 of x, and then you divide it by the square of the denominator, x square plus 1 whole square. So this is the expression. Now you can again solve this simply by again taking the partial derivative of this value now. So we basically utilized this value, I'll highlight it, we utilized this formula, you may say, to refine this expression into this form. Once we have this form, now we can take the derivatives from this. So now the derivative comes out to be, 4yz, and it is going to be the first derivative, which is minus 2x divided by x square plus 1 whole square. Okay, so once you have this, again we can use the expression to get the second derivative. The second derivative of this will be 4yz, and now x square plus 1 whole square minus 2 then you have negative 2 of x, 2 x square plus 1 multiplied with 2 of x divided by the denominator will be x square plus 1 whole square, which will be now 4 because I have taken the denominator square. So this is the equation that you have gotten. Now you just put the value of p for these. So 4yz, what is the value of x square? Once you partial derivate this, you will get minus 2 x square plus 1 whole square, and you solve the 2x's to get 8x square plus 1 divided by x square plus 1 power 4. It will come as it is. And now you put the values of p, so you should get so 4 into y is 2 into 3, so 6 4s are 24, and then in the bracket when you put all the values at p over here, it comes out to be minus 8 plus 16 divided by 16. So the answer comes out to be 12 for the first part. So we have taken the solution of the first part. Now let us go to the second term over here and do the partial derivative with respect to y. So now for the second term, we will have del square v by del y square is equal to del square by del y square. What is the value of v? It is 4yz x square plus 1. So it is 4yz x square plus 1. It is then it is with respect to y, so I can just take the first as 4 of z divided by x square plus 1, and you just take the partial derivative of y. So the first one will be y, for the second one it is going to be 0, so the answer comes out to be 0. For the third part, we take del square v by del square z, and it is again going to be del square by del square. Value will be 4yz divided by x square plus 1. So we take 4y outside and divided by x square plus 1. You take the square of z. So for the first one it will be 1, and then for the coefficient it will be 0, so the answer will come 0 for the second one. So it means finally my del square, when I add all the terms, will be 12 volts. And since I want to find the rho v, so it is going to be, so the value of rho v is going to be del square v is equal to minus rho v by epsilon. So it is going to be 12 is equal to minus rho v divided by 8.85 into 10 raised to power minus 12, and the answer comes out to be in terms of rho v, remember we are finding rho v, is equal to 106.28. so I'm getting the same answer, it's negative 106. So negative 106.28 into 10 raised to power minus 12 coulomb per meter cube. So this is what I am getting. Let us see if this is the answer or not. So it is negative 106.2 picocoulomb. Yes, it is 10 raised to power minus 12. So this is the answer to the equation or to the problem that we have solved, and hopefully you understood it. So again, it's all about how you solve the double derivatives, and it comes to you when you practice more. Now let us do the solution of the remaining two parts of this problem. So let us look at solution to part B. So in the part B, V is equal to 5 rho square cos 2 phi. So we, and at P is equal to 3 pi by 3 and 2. So the potential is 5 rho square cos of 2 phi at P having a value of 3, phi is pi by 3, and z equals to 2. So we need to find first potential at P. So you just input everything over here. So it is 5 3 square cos of 2 into pi by 3, and it comes out to be minus 22.5 volts. So this is the solution to the first part. Let us confirm It is the solution to the first part. Okay, now in the second part we need to find rho v. So again, using Poisson's theorem, minus rho v by epsilon is our main equation to solve, which means we need to find the del square v. In this case, del square v is for the cylindrical coordinates, so it means we have to use this complete equation to solve it. Now if you look at this equation, we can immediately see that this portion will be 0, because in the question we only have 2 phi and the rho value given, there is no z. So this means automatically utilizing this third part will be equal. So I'll just write the equation for the first two terms. So it is going to be 1 by rho partial derivative with rho partial derivative of v by rho plus 1 by rho square del square v by del phi whole square, and the third term is always 0 because there is nothing over here, so I'm just going to make it 0 in the question. Now this comes out to be, so del square v is now just input the value 1 by rho the partial derivative of v, then you have rho. What is v now? V in this case is 5 rho square cos of 2 phi, and then you have plus 1 by rho square, then the double derivative of this will be 5 rho square. Let's take the first derivative of this value. So derivative with respect to phi will means that you will have cos 2 phi, which will be cos is minus sine, and this is sine, so I can write minus 4 cos of 2 phi. So this is the solution which you get for the first one, and I can easily cancel out phi square with phi square. So now I'll have 1 by rho the first value of here. Let's take the partial derivative of this term, so it comes out to be 2 into 5 10, and cos of 2 phi, and then rho and rho becomes rho square, so it will be 10 cos of 2 phi, and for this term it is 5 into 4, it is equal to minus 20 cos of 2 phi, and then we solve this. So let me write the solution of this. It is 1 by rho, here the 2 will come outside, this is going to be 2, and then it is going to be cos of 2 phi, so the rho and rho can cancel out for the second part. So I've taken the partial derivative of rho, okay, that's why 2 has come over here, and this is minus 20 cos of 2 phi. Finally, when we put everything over here in terms of the values, so cos of phi is pi by 3. When you put in the value and solve it, the answer comes out to be 0. So once if this is 0, this means that rho v is going to be minus epsilon del square v, and this comes out to be 0. So this is the solution to the second part. I leave the third part for you as a home task. And again, the third part is quite straightforward. In the first part, you just input value of P over here to get V at P, so you should get 4 volts, and again once you do the Poisson's double derivative of the potential, your answer will also come to be 0. So please try the third part yourself. We are utilizing this equation for the spherical coordinate systems. Again, in the question, one part is not mentioned, which means that the element over here will be not considered, which means that we have r square and cos phi, so the theta portion will not be considered over here. The only part that is going to be utilized is going to be 1 by r square for this part, and then the sine square will be used over here. This portion will not be included when you are taking del square v, because the question doesn't contains the theta component. Hence, this is the solution to the problem, and this concludes our lecture on the 6th chapter.